We've already looked at optimizing single variable functions. Looking at this graphically is fairly straightforward to do. We just look for peaks or valleys on our graph, and we can identify those as a local max or a local minimum. We also looked at how to do that, how to work through our function, use derivatives to find and classify those points. And we saw that in some cases, we can end up with a point that is a critical value, meaning our first derivative is equal to 0, but the point is not a maximum or a minimum. The function in this case is increasing, levels out for a moment, and continues increasing. We're going to have similar ideas that we're looking for as we look to optimize multivariable functions. Obviously, this first graph that we have has a local minimum because that's the lowest function value that function ever takes on. In this case, this also happens to be an absolute minimum for the function, meaning that with multivariable functions, we can identify where maximums and minimums occur, but we can also find, similar to this case where we had a point that was neither a maximum or a minimum, we can identify points that are neither a maximum nor a minimum with three-dimensional functions, and we refer to these as saddle points, because if we could manipulate this graph a little bit, we could see even better. It essentially forms a saddle shape, a spot where a person could literally sit there, but the function's not taking on a maximum or minimum value. In order to do this, we're going to apply the second derivative test for functions of two variables. To do this, we'll start off by finding all critical values for a given function, and then we'll evaluate this value d, which we calculate as f sub xx times f sub yy minus f sub xy times f sub yx, meaning we're going to find all four of those second derivatives. We'll evaluate those second derivatives at each critical value that we identify. Once we plug them into this formula, we get a value for d, and then we interpret that result. The value that we end up with for d can be positive, so greater than 0. If that's the case, then the function has a local minimum. If f sub xx evaluated at that critical value, so the second derivative with respect to x, is also greater than 0, and we would say that the function has a local maximum if f sub xx is something less than 0. We also have the case where d is negative, so if we end up with a negative value for d, then we would say that the function has a saddle point, meaning that point is neither a maximum nor a minimum. And the last case that we have to consider is where we get a value of d equal to 0. In that case, the test is inconclusive. We don't know if the point that we identified as a maximum, a minimum, or a saddle point. We literally learned no new information, unfortunately, as a result of all of the work that we do. And all we can say is that the test is inconclusive, and further methods that are beyond the scope of this course would have to be employed to figure out what's going on at that point. We need to know how to classify all of these, but also recognize that in this last case, while the test is inconclusive, that is our final answer. We just didn't learn any final information about that critical point.